Thank you very much for that. And welcome everybody to the April meeting. Tonight is a joint meeting between the BGA, the EGGS and the BTS. Tonight's presentation is on Kilsby Tunnel construction, geotechnical and groundwater lowering. And we have two presenters for the evening. We have Mike Chrimes, who is Vice Chair and IC Panel for Historical Engineering Works. Mike is a former Director of Engineering Policy and Innovation at the ICE, working in the library of the ICE for over 37 years. He's written extensively on the history of civil engineering, including 3 books, The Civil Engineers, the Contractors and the Consultants, with Hugh Ferguson. He contributed a number of chapters to the 2003 biography of Robert Stephenson, edited by Michael Bailey. Our second presenter is Martin Preene, Technical Director at Coffey Geotechnics Limited. Is a groundwater engineering and dewatering specialist with more than 35 years' experience in delivering practical solutions to groundwater problems. A civil engineer by first training, he is both a chartered civil engineer and a chartered geologist, and has worked on projects in more than 40 countries and works as technical director at Coffey at the Tetra Tech company. Martin is a former chairman of the BGA and is author or co-author of more than 70 technical publications, including Syria, Groundwater Control Design and Practice, and Groundwater Lowering Construction, A Practical Guide to Dewatering, which is now in its 3rd edition. He's given lectures at a number of societies and at several universities as visiting lecturer and external examiner. So welcome to our 2 presenters, and over to you.
Thanks, Rod, and thanks for Martin for getting me involved in this. I'm Mike Chrimes. As Rod mentioned, I was working on a biography of Stephenson more than 20 years ago and dealt with the construction of the railways he was responsible for, including the London-Birmingham line. And at the time we started work, Professor Skempton was still alive, and he'd done some work for a book on case studies in geotechnical engineering that was never published. But one of his case studies was Kilsby Tunnel, and what a great story it is. Well, about 3 or 4 years ago, Martin got in touch with me because he'd known I'd been involved with that book and asked if I'd be interested in a paper because of his own specialist interest. And coincidentally, at that time, the ICE had received some more drawings of the tunnel, progress drawings of the tunnel, and I'd also come across a journal, an Austrian journal, which gave a contemporary account of the construction of the tunnel. So there was I won't say a meeting of minds, but at least a coincidence of interests, and the result was 2 papers, which hopefully you've all read. I'm going to just run through what we're going to talk about quickly. I'm going to talk a bit about the tunnel, its location, and then about the tunnelling, how the work was carried out, how the project was organised, and, if you like, the history of the pumping and groundwater lowering in the 1830s, and Martin's going to take it from there and give it some real modern flavour. So Kilsby Tunnel, for those who don't know it, it's under the Northamptonshire uplands. It's towards the northern end of the London-Birmingham Railway, and it was really on the route because the tunnel was enabled a steady gradient to be maintained through the line, and they were very keen on minimising gradients for locomotive traction at that time, so Kilsby was there on the route. So, it was built 1835 to 1838. Robert Stephenson was the engineer. It was his first major project and really made his reputation internationally. Kilsby was contract 7F. The contractor originally was Joseph Knoll, who came from a family of established contractors. It was one of 6 tunnels on the line, but by far the longest, and at the time of its construction, the longest railway tunnel in the world. Because of the problems which we're going to come to, costs escalated, they trebled. It was the biggest overrun on the line, which was full of overruns actually. And the major challenge was quicksand at the southern end, a large bed of it, which was unforeseen. And these problems were solved by means of an extensive groundwater pumping exercise, which was unprecedented for the time, and coupled that with careful observations which enabled Stephenson to work and his team to work a way through. So, the project, London to Birmingham Railway, its organisation really followed the typical organisation of construction contracts that have been in place certainly since the time of Smeaton on the Forth Clyde Canal, where you had the engineer, you had generally then for infrastructure projects, a committee of proprietors, and then under the engineer there'd be a group of resident engineers, assistant engineers in charge of parts of the line. And in this case of this line, there were committees at the north and south at the Birmingham and London end, and there were assistant engineers, Gooch, Forster, Crosley, Buck and Fox, covering roughly equivalent sections of the project. So Gooch was at the top and Fox in the end at the bottom. Crosley and Buck were very experienced canal engineers, much more experienced than Stephenson at the time, whereas Gooch and Forster were more or less contemporaries of Stephenson, and Gooch had been George Stephenson's amanuensis on the Liverpool-Manchester. Like most of these projects, there were surveys carried out. The surveys had begun in the 1820s, and 2 rival companies were trying to get an Act of Parliament through. In the end, it was the Stephenson route that prevailed, although the first bill they put forward was unsuccessful. And once the Act was passed, they moved fairly quickly. They appointed engineering staff rapidly, and Stephenson himself walked the line 12 times before work really got going. So he knew the route intimately and the likely hazards. And of course, once you've got the Act through, you can start acquiring land, and those familiar with things like HS2 will have a feel for that kind of challenge. Well, Stephenson's decision was to let the lots in relatively small lengths because he was concerned about the capital resources of the contractors. And I think the size of the contracts actually put off the more successful contractors because there wasn't enough money involved. But Kilsby Tunnel was pretty evidently going to be quite a challenge, so it was a contract on its own. Most of the contractors had considerable experience, including Knoll. The contracts were let from May 1834 to December 1835, and they started with the north and southern end because they wanted to get traffic moving as quickly as possible, and detailed specifications and contract documents were provided so the contractor knew as much as the engineer knew about what the job involved. And this was the approach that Brunel directly copied on the Great Western and elsewhere. Many of the contractors failed or ran into financial difficulties, including at Kilsby, and these were generally due to the ground conditions. So, a bit of context, transport tunnels before Kilsby, well, it had 70 years of the canal age, really. and there were at least 10 canal tunnels that were longer than this, and many of them had had problems. And interestingly, Stephenson had only envisaged 6 shafts on the length of this, and all the precedents really had far more working shafts involved. If you work out the time he thought it would take, and the 6 shafts might have worked, but they didn't really take account of the geology. And there was also an enormous difference in the kind of pumping and access equipment used. So in the canal age, really portable steam engines, sort of steam engines you could move around on site, prior to 1800 weren't really available. So most of the tunnels were worked using horse gins to get material in and out. This is a drawing from about 1820. But by 1820, tunnelling had come on quite a way, and there were 3 tunnels built around that time by Pritchard and Hoof, who were contractors who worked on a different length of the London-Birmingham Railway, who proved very experienced. And on the Strood Tunnel and Harecastle Tunnel, which were 2 of the longest, they had, hopefully you can see here at least, they had some dismountable centering, and these tunnels were built in space of 2 or 3 years, whereas many of the 18th century tunnels had taken considerably longer. So tunnelling had moved on quite a lot. Perhaps the application of steam power less so, but certainly the contractors knew what they were doing by this stage. And the Stephensons themselves, they'd worked before on Kilsby, apart from their mining experience, on 3 tunnels. You can see a drawing here, a section through the Wapping Tunnel, show really an indication of the care taken in mapping the strata and the location of the shafts in the 1820s. Wapping was reasonably successful. Canterbury, on the Canterbury and Whitstable Railway, was completed before Kilsby began. But the tunnel on the Leicester-Swellington Railway hit difficult ground conditions, which really anticipated the sort of problems that Stephenson faced at Kilsby. And the initial contractor failed, and the supervision of the engineers was not up to scratch. That is a bit of a contrast with what we'll discover about Kilsby, really. So Kilsby, a lot of experience here. Stephenson was a mining engineer. Frank Forster, in overall charge of the section, was a mining engineer for North East. Charles Lean, who was the junior engineer in charge of the Kilsby Tunnel itself, came from a family of Cornish mine engineers. And the Knoll family, they were very successful contractors. They've been particularly commended by Telford for their work on the Macclesfield Canal in the 1820s. So everybody knew what they were doing, and everything looked set fair. And just as a reminder, I think an important characteristic of Robert Stephenson is he was a team player. Many of you will have seen this painting, I'm sure, in the building. But there's Stephenson. This is Frank Forster, who was his number 2 in this area. And this chap Hemingway was one of the people who worked with Knoll. He was a mason, and he worked on the towers of the Britannia Bridge. And you've got the directors here, so Stephenson had to work with the directors, and there were various labourers and things. So the picture of a team is the picture you should take for the approach, really, to this tunnel. And a reminder again, where the Kilsby Tunnel is, and where the bed of... this is where the quicksand was discovered. Here, and here are the portals. And it's going through an upland area, which you can probably see the relief better here. So the OD for the base of the tunnel is about 120 metres, and it's about 40 metres below the level of the top of the Kilsby Hill, for want of a better description. You get a bit of a feel from this. This is from the original parliamentary bill, the survey, and you can see here the level of the tunnel at the bottom of the hill. This is obviously an exaggerated scale, and the tunnel was 27 foot 4 inches high and 24 feet across. So it was designed for double track working from the start. And Forster was in charge of the boreholes, and the first borehole he did here, and the other one about here. And if you think that they're more or less on the line of where the tunnel was to be excavated, so he found continuity of strata, which we'll see again in a minute. And so they had no reason initially to panic about whether they were going to hit anything awful. I mean, it was a long tunnel. They knew there might be some problems. But they felt the strata would be continuous, and so they began work. And the first thing they drew up, or Stephenson's team drew up, was a specification and drawings for the tunnel. So the drawings showed the portals, cross-section of the tunnel to be, how it was to be built, with details of the lining, etc. And so you can see here, initially, it's a sort of 9 to 18-inch lining, and they were using a lime that had some pozzolanic qualities with sand, puddle clay backing, and they had skew backs, which I'll show in a later drawing, on which they built off the brickwork, with 6 working shafts, 2 ventilation shafts, and air shafts were to be built as required. And it should be noted that although there were 6 tunnels, the specification varied slightly. So Stephenson was aware that the ground conditions varied from tunnel to tunnel. They weren't all exactly the same. What they were expecting the contractors? Well, as built, it's a 27-inch brickwork lining. They used Roman cement because of the water, really. The backing's there, the skew backs are there, but there are 20 working shafts. The ventilation shafts are the same numbers and the air shafts. So if you want to see initially why it cost a lot more, well, there's a lot more stuff going on. And this is a cross-section through the tunnel just showing the geology. And once they decided to award the contract, Forster did some more boreholes or trial shafts. They were big enough to see the strata, so they're proper shafts. So one here, one here, one here, and one here. And lo and behold, the closest ones miss this quicksand. So they think everything's going to be good. And the sort of things they'd have used are these boring tools shown here. They might be seen slightly inadequate for today, but it's not the fault of the boring tools that they've missed this quicksand. There was an element of being unlucky. And just to give you a flavour, these figures here are taken from the drawings in the ICE, and they give the strata quite detailed. So these are the trial shafts. This is trial shaft 1 here. So you've got obviously the soil at the top, and strong marl at the bottom, dry blue marl, rock with the parting, a bit of water in there. But again, nothing they wouldn't normally think they could contend with. So these were quite good ground investigations, given the number that they dropped in. Anyway, so how was the thing to be proceeded with? Well, the first thing would be, once you've got the shaft in place, you do a 10-foot top heading, timber it out, so there would have been a bit more timber support here, and then gradually open out, fully support it, and then start at the bottom, building the brickwork. These are the Bramley stone skew backs, and then slowly fill it in at the top, and then put the formation in and the drainage, cast iron drain in the middle. So this would be now considered, I suppose, what was called the English method of tunnelling. Interestingly, the specification doesn't mention the use of crown bars. If we look on the next drawing, it is just possible with those very keen eyes to see that there are inevitably timbers going longitudinally. But this basically, when the shaft came down, they timber up on both sides. They build it up, so complete the brickwork on both sides before they put these cast iron curbs in supporting the shaft. So they would support, all this area would have been supported till there was enough brickwork in place at about 6 foot each side of the shaft coming down to minimise the risk of collapse at that time. And they would have proceeded as here. So this side, once the timbering was done and the heading opened out and everything, the brickies would have been in building up on this side, and then they started on that side. So those doing the excavation, the miners, weren't interfering with the team there. And that's how things were meant to proceed. And you get a bit of a sense of the scale of it from this. This is a view that was taken in July 1837. You see horses down the bottom. They got the rails in place to move stuff around. There's allegedly 2,000 people working on the tunnel, 200 horses, and perhaps 13 steam engines and a number of horse gins as well. And you can see just about here a man coming up with taking up a bucket of spoil. So labour intensive, some mechanical support. So the shafts were sunk in to a depth of 10 foot, and then they bricked them up in sort of 6 to 10 foot lengths as they went round. And the two ventilation shafts were absolutely enormous. They were supposed to have contained 1 million bricks, and they were taken down to formation level because they couldn't see how they could support these. They were 60 foot in diameter, how they could support the weight on the crown of the tunnel. So they were taken right down to the bottom. And the view over here shows the headgear for moving plant and stuff. So the ventilation shafts were used as well to move stuff up and down from the tunnel. And before I get on to the groundwater issue, there were other issues with water ingress on the tunnel. And Lean, allegedly, well, certainly, saved a group of miners. Where one section had been flooded, they started using a raft, floating it along and getting the bricklayers to the front of the excavation and start bricking it up there, supporting it there from a raft as quickly as possible to prevent collapse. Well, some water inevitably came in before they'd finished their work, and they were in danger of drowning, but Lean swam from the nearest working shaft and supposed to have hauled them with a rope between his teeth back to the working shaft and saved them. There were 28 people died on the job, so he didn't save anybody. Anyway, the great problem very clearly was with this bed of sand that we've seen on the section. So Forster's boreholes didn't really give a clue as to the likely danger of quicksand. And in May 1835, the contract was let, and soon afterwards, Noel got on site, and he began sinking 4 shafts, and he put up a steam engine, which was probably to deal with what anticipated pumping, but also to bring stuff up from the working shafts. But in September, they hit a bed of quicksand from working shaft 2, and the usual method of dealing with something like this would have been to drive an adit, perhaps have parallel drains along the tunnel as they've done with some of the canal tunnels nearby. So they did try a couple of drainage adits, but they almost immediately blocked up with sand, and no water came out, so they had to think again. So they were wondering what to do. Stephenson realised they needed some pumping power, so they ordered 2 more steam engines, 20 horsepower and 25 horsepower, but they took some time to get on site. They tried looking for an alternative alignment, but there were basically Forster couldn't find a better route through the Kilsby Hill, and if they went somewhere else, they'd have needed another bill, and they would also probably have lost the confidence of the shareholders, and the railway scheme might have been sunk, so they persuaded the directors that the best thing was to keep on at it. And I think at that stage they thought they'd just pump the quicksand dry. The typical mining solution, if you like, at that time would just pump, and hope the thing went, to an extent, went away. So they realised they could increase the effectiveness of the pumping engines if they used a flat rod system, which I'll show a picture of in a moment, which meant they could have more than one shaft operated from the pumping engines, and also they could be off the line of the tunnel, not interfere with the tunnel working as well. So it was it was well-known technique certainly in Cornwall at the time, so it might have been Lean who suggested it. Well, Stephenson was a bright enough guy to have thought it up for himself, I'm sure. So in January 1836, they got a pumping engine going, they start pumping, and Knowles, relatively elderly, and he suffers a heart attack. In some accounts it suggested it finished him off, his health, but I think the real problem with the contractor was that Knowles' death meant they had no capital, they had to sort out his estate, so they couldn't carry on. So it really fell to Stephenson and Lean to work out what to do, and in a sense Stephenson becomes the contractor. It's a direct labour job, and he does the sort of things you'd expect a contractor getting first onto site to do. Build a railway over the hill so he could move people and muck around and equipment. Have more working shafts so you could maximise what's going on in the dry bits of the tunnel while they sort out the quicksand problem, and power those in the deeper sections with 6 additional small horsepower engines, with a larger one to act as a mortar mill for brick making and cement making. And at that stage, I think he thought they needed 20 million bricks. Well, they needed a lot more than that in the end. So they sunk pumping shafts off the main tunnel alignment. They were sunk with timber tubbing rather than with brick lining. They reached rail level after 6 to 7 months after they'd started work. So it took a long time before they started to really get going in the quicksand. And they began sinking the shafts into the quicksand in November, and then began tunnelling in December. And you'll hear a bit more about how that became possible from Martin. But the amount of water they were pumping out, 1,800 gallons a minute, 136 litres a second for 6 months. And so it went on. There were inrushes. It wasn't really until the tunnel was finished that you could say it was safe safe from collapse. And just to give you an impression of the additional, there were originally meant to be 6 shafts on the line of the thing. So, 1, this is the quicksand area here, 1, and then 2's over here, and then you go up to, 2, and then 3's over here. Got the main, one of the big ventilation shafts here. You've got pumping shafts. It's a bit misleading really, because the pumping shafts are off the line. So it looks as though it's more cluttered than it is. But once they got working, they put in these additional working shafts, 1A, 1B, etc. So they could be very, very busy in quite short lengths, which would also have had the advantage if something went wrong with one of the shafts, there'd still be other shafts they could work. So, but there we are. A tremendous civil engineering achievement. These are the kind of pumps that they were using. So the steam engine cylinders driving a piston up and down, activating a beam, which is pumping, and there's a valve down the bottom so that as the suction pulls the water up, it doesn't drop back down. So that's the sort of mechanism, and there's a fantastic Bourne engraving showing really what's going on here. So you've got the horse gin here, which would have been For the horse gins were used particularly on the shallower shafts. Then you've got this flat rod system, so you could drive pumps at some distance away from the steam engine, wherever you wanted to put them really, and you can get a better feel from it here, and then it's going up and down the shaft. And the Austrian journal I referred to, this is more or less a reproduction of, at a much better scale, of what Francesconi, that engineer, described. So this is what sort of helps make sense of what we can see here. I think Bourne's pretty accurate, really. So I think it's a well-organised project. They overcame the problems, and you'll hear a bit more about that in a minute. It was a great team, and I'm just to give you a flavour, and I'm just going to end with a couple of quotations here, just to put what Martin's got to say in some context, really. So, this is for the bricklayers. Even while under the protection of the immense pumping power, it often happened the bricks were scarcely covered with cement, ready for the setting, ere they were washed quite clean by the stream of water which poured down overhead. The men were accordingly under necessity of holding over their work huge whisks of straw and other appliances to protect the bricks and cement at the moment of setting. And they were using Roman cement by that stage, and that was very quick setting. So you can imagine if that's been washed off, how difficult their work was. And just to visualise the water itself, the bulk of water, if allowed to flow for 3 hours only, it would fill a lake 1 acre square to depth of 1 foot, a total nearly equivalent to the contents of the Thames at high water between London and Woolwich. That's from the words of LeCount, who's one of Stephenson's assistant, contemporary thing. And he also observed, just an indication of the geological understanding of the time of Kilsby, organic remains at Kilsby are very numerous. In some parts of the excavation, there's hardly a cubic inch without shells and other remains presenting themselves to the eye. And as the earth taken out has been principally laid into spoil, there'll be ample opportunities for some time yet for further examination, which will repay either the scientific inquirer or the cabinet collector. By that I think we mean the amateur geologist, who's basically whose observations were the basis of geological knowledge at that time. Anyway, I'm going to ask Martin to take it on from here, and you'll all understand much better what Stephenson had to do.
Thanks, Mike. Good evening, everyone. So I'm going to talk about the geology and the groundwater issues, specifically the geological context. I'm going to talk about some actual hydrogeological analysis that Stephenson did, and finally I'm going to ask the question, was groundwater lowering the right solution? Were there any alternatives? So Mike's shown this before, which is based on the work by Professor Skempton, but I think it's true to say that with modern knowledge, the geological problem is easy for us to understand. Most of the tunnel is through mudstone-dominated lias bedrock, quite a benign tunnelling medium, and the quicksand problem is an area that we call a buried channel, which is filled with glaciofluvial deposits, and that's the heart of the quicksand problem. Above the buried channel, there is a blanket of glacial deposits, mainly till near the surface. The bedrock itself comprises the Milestone Rock Formation, which it forms the top of the hill. That overlies the Durham Formation, and then the Charmouth Mudstone Formation is present round about tunnel invert level. And those are mudstone-dominated strata, though the Durham, and particularly the Milestone Rock, have got quite a bit of limestone beds in them. Interestingly, sections C2 and C3 of HS2 at the moment are constructing several structures through the same geology. So the question is, how do we know? What information do we have about the geology? And we actually have the as-built geological records. That there is a digitised version of a long section from the 1830s, and that is the actual paper copy laid out upstairs in the library.
And any of you who've ever logged a face or you've tried to convert daily records into a record of what the tunnel's been through, you can totally get what these people have had to do. You can see how difficult it is to read at any scale. You know, it's a bit of a legend there and so on, because you've got a very long linear structure. The coloured pencils, have been out and so on. But obviously, when you get it in your hands, it's tremendously impressive and actually very informative. We can't see much at this scale, so we've zoomed in, and this is the quicksand section, and the tunnel is there, and I don't know if you can see, but there's actually sort of progress records there where there's numbering, and there is a version of this where dates are allocated to see how progress was done working out from the shaft. And you can just see that the dotted pattern there is broadly representing the quicksand, but it's very busy and so on. So for our paper, we produced a simplified version where we put less information on it and also expanded the vertical scale. And you can see that the tunnel is broadly driven through the mudstone bedrock, and you have the channel of sand. And interestingly, the channel doesn't really reach invert, or it only does over a short period. So a classic scenario of all the bad wet ground is in the crown and in the shoulders, just where it's really difficult to deal with. So if we're planning this project today, obviously we have access to modern information, and we're very lucky in the UK that the BGS, the British Geological Survey, has great information on the UK. So here we've just applied the tunnel route to modern mapping. That's the tunnel there, and the grey area is the quicksand zone. This is a bedrock map, so you can see the top of the hill is capped by the Marston Rock Formation. Most of the hill the tunnel goes through is the Durham Formation, and then at either end, roughly at rail level, it's mainly the Charmouth Mudstone Formation. But we've already sort of told you that it's a glacial strata that's causing the problems, so the BGS has the superficial deposits, and you can see the route here. And the sort of pale blue colour here is the glacial till, in this case the OB member, and the sort of pinky or lilac zones are essentially more granular materials. So it's true to say that down here where there's a quicksand problem, at the surface there is some sand and gravel or granite deposits around. But it's not, I don't think even if you had modern information, you would automatically think that there was a big channel of buried granular material there. But I think you would possibly pay attention and maybe investigate in that area, because you'd use the mapping to help direct and inform your planning for the boreholes and so on. Stephenson obviously didn't have that opportunity to use that information, and the project boreholes or shafts missed only by a little bit the problem ground. I mean, probably a few people in this room, like myself, think we have, during our career, encountered unforeseen ground conditions, but I think Stephenson has a pretty solid case, as we'll talk about in a moment. Because obviously with modern geological information, we understand that the North and Midlands of England experienced glacial conditions during the Quaternary period. And this diagram over here shows the various glacial extents. This line here is the Anglian glaciation, which is the furthest southward extent of the glaciers during the Quaternary period. And you can see here that Kilsby is in the area that was glaciated. Of the three glacial extents on here, the Anglian's the oldest, the next youngest is the Woolstonian, that didn't get as far as Kilsby, and then the Devensian, the most recent one, actually finishes quite a way further north. And so because we know that the UK has been glaciated in its northern parts, we know that the movement of the ice has left behind a potentially variable layer of superficial deposits that we term the glacial deposits. And a really key issue is that the bedrock profile might not follow the ground surface, because the advance and retreat of the ice is very abrasive, but then as well you can sometimes get glacial lakes dammed behind ice that can be suddenly released, and you get erosion channels associated with the bursting of ice dams. So you get scenarios, and I've encountered many in my modern career, of buried channels in the bedrock below the superficial deposit. And even today, they're nearly always bad news in groundwater terms. But that's modern knowledge, so we need to put ourselves back to the 1830s. And the 1830s was a time of rapid development in geological knowledge. And in the UK, it was actually driven, broadly speaking, by the construction industry. Land drainers, canal builders, they sort of exposed lots of geology. And William Smith famously produced the first map representing the surface geology of the UK. And if you've not read the book, The Map That Changed the World, it's quite an interesting story, both about the map and about Smith himself. And this is one of the versions of Smith's map. There's no evidence that Stephenson directly used Smith's map, but it's quite clear from Stephenson's general methods of working that he and his advisors will have consulted experts with local knowledge, and they will have used the most relevant information. So the question is if we can look at Kilsby on Smith's map, how does it compare? And in terms of the bedrock geology, Smith's map is spot on. So there's the Kilsby Tunnel, and it's in something known as the blue marl of the lias, which, you know, nowadays we'd think it would be a mudstone or a marl. Pretty accurate description of the bedrock conditions that Stephenson encountered, and again a relatively benign tunnelling medium, which is what he actually encountered over the majority of the tunnel length. And what's interesting, and it didn't really strike me until I was quite a long way into researching this, was that the contemporary reports discuss the groundwater problems almost solely in terms of bedrock. They assume that the water's come from the bedrock, whereas in fact, in reality it isn't. It's a much younger strata of glacial deposits. And this is a really key point, again, that I hadn't understood, that the nature and the origin of glacial deposits was not well understood in the UK in the 1830s. And we now know that if you work anywhere north of the Midlands, that glacial deposits or glacial effects, including periglacial effects, are possibly going to affect your project. And it's routine to deal with that. And here's a recent Geological Society publication on just that matter. But in the 1830s, glacial theory, as it was known, because it was a theory, was not an accepted concept in UK geology. It's pretty amazing to think that in the early 19th century, many experienced geologists subscribed to the diluvial theory, where the superficial deposits were termed diluvium from the biblical flood, as in diluvium, deluge. And there are papers about the conflict that many clergymen, who are also geologists in their spare time, had when glacial theory subsequently arrived. And glacial theory arrived after Kilsby. The first serious consideration was probably a meeting in 1840 at the Geological Society of London. Here's the original record. And at the meeting, the Swiss paleontologist Louis Agassiz presented his paper, which was called On Glaciers and the Evidence of Their Having Once Existed in Scotland, Ireland and England. And again, glacial theory was not instantly accepted. There was no eureka moment. But in the following decades, British geologists accepted that the evidence of erosion, transportation, deposition of superficial deposits in the UK could be explained, indeed, by this theory. But then, how does that relate to construction? And even at the end of the 19th century, the actual impacts of glacial deposits on construction were not widely recognised. Professor William Boyd Dawkins was a very eminent 19th century geologist, and in 1898 he gave his James Forrest lecture to the IC, I imagine, in this very room 126 years ago. And his lecture was on the relation of geology to engineering, and he said, at first sight, it would seem improbable that geological theories connected with the Pleistocene age and the glacial period should have any relation to engineering work. Nevertheless, they have a most important bearing on engineering results in connection with the superficial accumulation covering the solid rocks over a large portion of the British Isles. So, viewed in the light of the absence of understanding of glacial theory, Stephenson's problems, absolutely are unforeseen ground conditions not predicted by his team or encountered by precision borings. It seems, like Mike said, just bad luck or random chance that borings missed the buried channel of sand. And I know David Hartwell's in the room, and David Hartwell, I believe, worked on a project in the 90s where the boreholes missed a buried channel in a rock tunnel and caused various problems. In the paper we do talk about how there's still modern parallels to this. Another really fascinating thing is that Kilsby Tunnel, the problems helped explain themselves, by which I mean that the groundwater problems are so widely reported, subsequent geologists in the 20th century actually used that information to better understand the geology of the English Midlands. In the 1950s, Professor Fred Shotton postulated existence, for part of the Quaternary period, a very large glacial lake independent of the current river system, which covered large parts of the English Midlands. And Shotton named this lake Lake Harrison after W. Jerome Harrison, a pioneering figure in Midland glacial geology. And myself and my colleague Steve Buss have superimposed the postulated extent of Lake Harrison on modern topography, there's also the Anglian glacial extent here and a Woolstonian glacial extent here. You're probably wondering, why is Martin talking to me about a lake I've never heard of that doesn't exist anymore? And the answer is that Lake Harrison is very probably the cause of the problem. Because if you look, the Kilsby Tunnel is here on the boundary of the lake, on one of the sides where it's not bounded by ice, it's bounded by the high ground. And the Kilsby buried channel is postulated as an eroded spillway channel from the drainage of this lake. Later work in the 1980s, it's worth saying that Shotton's work is slightly controversial among geologists, as I understand, but later work in the 1980s said that maybe there wasn't a single large lake, maybe there's a series of transient ice marginal lakes, but they still agree that Kilsby fits the profile of being an outflow channel. So that's the geological bit. Now let's do a bit of geotechnics. And like Mike says, Stephenson was all in on this project, and by the time he was committed to dealing with it by pumping, it must have been a daunting prospect to try and drain the whole of the quicksand. And there was no analytical tools to hand, never mind no computers, there were no equations. Darcy's law, I'll talk about in a moment, was still 20 years away. But Stephenson used observation and logic, presumably, to understand the effect of pumping from widely spaced wells, and he deduced it was not necessary to drain the entire body of sand. And again, Stephenson wasn't a prolific author of papers, unlike others, and so he didn't really write up Kilsby, this aspect at the time. But several years later, he was working on the water supply to London, looking at some abstraction from the chalk in some areas. And he actually, in the 1841 reports about the water supply of London, he talked about his observations, personal observations at Kilsby, and he said, so we talk about pumping from shafts. I was soon much surprised to find how slightly the depression of the water level in the one shaft influenced that of the other, notwithstanding a free communication existed between them through the medium of the sand, which was very coarse and open. It then occurred to me that the resistance the water encountered in its passage through the sand to the pumps would be accurately measured by the angle or inclination which the surface of the water assumed toward the pumps, and that it would be unnecessary to draw the whole of the water off from the quicksand, but to persevere in pumping only in the precise level of the tunnel, allowing the surface of the water flowing through the sand to assume that inclination to which it was due to its resistance. Very wordy, but I'll explain to you what this means and why it's relevant. So here we have the sort of thing you might see in a textbook. We've got our Kilsby Tunnel being dewatered in this case by some hypothetical shafts on either side. And we all know that if the dewatering works, we draw down the water level at the tunnel, but we don't draw the water level down an infinite distance either side. We get something that we might term a drawdown curve, and we know if we go a certain distance away, the water level will eventually get back towards its original level. Stephenson proved this. He installed some distant monitoring wells 180 metres from the tunnel and showed that after 12 months of pumping while the shaft was dewatered, the groundwater level there had hardly been reduced. And he wrote again in 1841, the simple result, therefore, of all the pumping was merely to establish and maintain a channel of comparatively dry sand in the immediate line of the intended tunnel, leaving the water heaped up on each side by the resistance which the sand offered to its descent to that line on which the pumps and shafts were situated. And so Stephenson concluded that the water flowing through a granular soil had to have some sort of driving force. There was a resistance. And so when you abstract at a certain point, at a well or a shaft, the water flowing to that level has to have some energy to overcome that resistance. And the way that driving force or energy is provided is that the groundwater level or head at the distant point must be higher than at the shaft, and that's what drives the water towards the shaft or the well to overcome the resistance. And Stephenson's observation of the gradient of the lowered water table, that we'll call the hydraulic gradient, predated theoretical formulation of groundwater flow, including Darcy's law, by more than 20 years. But I've applied, compared with modern theories, including Darcy's law, and we can understand how prescient Stephenson's work was. So I've mentioned Darcy's law, and hopefully most of you have heard of it. Darcy's law is a really fundamental equation in geotechnical engineering, but it's not actually of geotechnical origin. It actually comes from the field of public health engineering. And it was developed by the hydraulics engineer in France, Henri Darcy. And he wrote in 1856 a report. I'm not going to butcher the French, but his report was basically in English, The Public Fountains of the Town of Dijon. So it's surprising that we're using information from that in our geotechnical analysis. But he had various vertical columns of sand. This is an illustration from the original report. And he was observing the flow through the sand vertically, and he related the flow rate to the hydraulic gradient. And he developed an equation, Darcy's law, that related flow through the granular medium to the applied hydraulic gradient. And the relationship between the applied gradient and flow was linear. And he then developed a coefficient of proportionality that modern engineers call permeability, and geologists sometimes use the term hydraulic conductivity. And there is an argument that before Darcy's law, the term permeability wasn't a concept. So it's pretty fundamental. This is Darcy's law expressed in an equation. And the reason for saying groundwater, it's the only equation you need to try and remember because it's the underpinning of everything else. It's a deceptively simple equation, and it's fundamental to geological engineering. It's normally expressed as the groundwater flow rate Q is equal to the product of permeability K, permeability also being known as hydraulic conductivity. So Q is the product of K, the hydraulic gradient I, and the cross-sectional area A. The negative sign is really important because it means that groundwater logically flows from high head to low head. It flows down the hydraulic gradient. We can also express the hydraulic gradient in terms of a head difference delta H and a flow path length L, and that therefore tells us that the hydraulic gradient is actually the slope of the water table at any particular point. So if we try and visualise that in terms of a tunnel with wells either side, I drew this diagram to illustrate a sort of a theoretical thing in a lab and the real world scenario. So this is in a lab, and imagine that we have our reservoirs of water either side with a high head, and we just add water in to keep it topped up. But in the middle, we have our low head. This is where we're dewatering the tunnel, and we're taking some water out. Just by conservation of mass, the water flows in from both sides into the middle, and basically this flow is determined by Darcy's law, and we have a hydraulic gradient there. And then in the real world, even though this is very schematic, we have our dewatering system around our tunnel, we've lowered the groundwater level here, and we have the water flowing here. The reason this is a curve, the hydraulic gradient's a curve, and it's a straight line here, is because the geometry is different, but the principle is the same. The point is the hydraulic gradient is the slope of the water table at any given point. So how do Stephenson's observations relate to Darcy's law? Because Stephenson does not use the term permeability or hydraulic conductivity. He uses the term resistance, and he stated, leaving the water heaped up on each side by the resistance which the sand offered to its descent to that line on which the pumps and shafts were situated. And mathematically, the resistance is the inverse of conductivity. So we can express the resistance here as 1 over K. And we can rearrange Darcy's law that shows us the hydraulic gradient. I won't go through the maths, but we end up with the hydraulic gradient is indeed proportional to the resistance. And so, based on observation, Stephenson expressed in words rather than mathematics essentially the fundamentals of Darcy's law 20 years before. So there is an alternative timeline. If Stephenson had been better at writing up his site notes, we might be talking about Stephenson's law and hydraulic resistance instead of hydraulic conductivity. So the final part of the talk is I just want to just evaluate the use of groundwater lowering, because the Kilsby Tunnel in 1835 to 38 is widely quoted in literature as being the first application of pumped well groundwater control. That's not strictly true, because a few years before, the elder Brunel at Mark Isambard used groundwater lowering when sinking the Rotherhithe shaft. And also in 1830 at Westminster New Bridewell Prison, not so far from here, just near St James's Park, Robert Abraham specified that groundwater levels should be lowered using an 8 horsepower steam engine to provide dry working conditions. But these are pretty small scale. And there's no evidence that Stephenson and his team were aware of these applications. But what they were aware of was nearly 100 years history of quite significant pumping from mine shafts. But I think in terms of construction, the work at Kilsby should be recognised as the first large-scale application of groundwater lowering on a construction project anywhere in the world. And the principle of the operation is essentially to pump from multiple locations, multiple shafts in this case, wells in modern parlance, and that would lower the groundwater level. It's the same approach we use today. The only difference is today we would use, generally speaking, electrically powered pumps, not steam engines. And electrical submersible pumps are actually first used in dewatering on the Berlin subway in Germany in the 1920s. And finally, was groundwater lowering the only solution? At the time of the works, were there any alternative to groundwater lowering by pumping? Because this time, the early 19th century, was a very dynamic time in terms of technique. So I've come up with some other options. And interestingly, most of these 19th century techniques are still used by people in this room today. So first thing is, we could have sunk the shafts as caissons maybe. Caisson sinking, we build a cutting edge, and then you build your structure above the cutting edge, and nowadays you jack it in the ground. Back then you would have put Kent ledge on to weigh it in the ground, and your structure would have been masonry, brickwork, or cast iron tubbing. And obviously by sinking it as a flooded or wet caisson, you would have counterbalanced the quicksand if you did it right. I think it's been pretty hard sell. You've got the hard glacial till above the sand, and even if you sunk the shafts, you wouldn't have really dealt with the tunnelling. So I'm giving that a no. Compressed air, who doesn't love a bit of compressed air? And it's been around a long time. It was actually patented before Kilsby in 1830, and obviously the principle of compressed air is we pressurise a confined space, such as a tunnel face or a shaft bottom, to try and counterbalance the water pressure and support the ground. But at the time of Kilsby, it hadn't been used in the UK and not really on a comparable project until the 1850s. The approach at Kilsby was a pumping approach, but for groundwater control we can sometimes go for the exclusion approach. And exclusion approach basically would involve trying to install some vertical barriers either side of the tunnel. So essentially we're isolating the tunnel by towing into the mudstone bedrock below. We then do a limited amount of pumping inside here, and we keep the water level high on the outside. Dramatically reduces the pumping volumes. One of the challenges is that this, at its deepest, the mudstone's about 40 metres down, so it's a pretty challenging depth to get a cut-off method down to. An option we might think about today would be steel sheet piles. In the 1820s, cast iron sheet piles were in use. They've been available for a little while. They'd taken over from weaker timber sheet piles, but there's no way they'd been able to driven to the required depth. We could have permeation grouted, and cement-based grouting had been developed in France in the preceding decades, but it wasn't applied in the UK until the 1850s after Kilsby. In any event, the sands were probably too fine to be dealt with by cement-based grouts, and the more effective and more penetrating chemical grouts weren't developed till much later. One of the first was the Joosten process, patented in Germany in 1925. Ground freezing has undergone a bit of a renaissance in the UK at the moment for various cross passage at Silvertown and other places, but it's a 19th century technology. It was first documented as being used on mine shafts in the UK from the 1860s onwards, but obviously it wasn't available at the time of Kilsby. So now Mike and I agreed that we conclude with going through Stephenson's many achievements. And the first thing is that in terms of project management organisation, the London-Birmingham Railway was a model of project planning organisation. Stephenson had an experienced team, and he recommended established tunnelling techniques suitable for the conditions expected. But the methods weren't suitable to the quicksand conditions he encountered, and decades of canal construction have shown how difficult it is to work in such bad ground. But after the early shaft sinking works encountered the quicksand, Stephenson and his team, they drew on experience in the mining industry, and they developed the solution using multiple steam engines pumping from shafts. They used flat rod systems to transmit power horizontally to minimise the number of engines that needed. And Stephenson established a large-scale groundwater pumping system, unique for the time, to lower the groundwater levels and stabilise the quicksand. The reported pumping rate was 136 litres per second for several months, and ultimately, despite cost overruns and delays, the tunnel was constructed. So, in terms of geology, the modern geological information tells us quite clearly the bulk of the tunnel was driven through this benign tunnelling medium of the middle ice bedrock, but 400 metres of the tunnel was through a buried channel of water-bearing sand of glacial origin, the true cause of the quicksand. But in the 1830s, the impact of glacial process in the British geology was not widely accepted. And I'm not convinced that even Stephenson, as the premier engineer of his time, would have known about such arcane and controversial theories. So I genuinely think that based on the knowledge of the time, Stephenson encountered unforeseen ground conditions and the quicksand zone was missed by his borings. But despite the lack of existing methods of analysis and so on, observation and interpretation, which is at the heart of tunnelling methods, of the behaviour of the ground, let them navigate through the problems, and the groundwater lowering methods were used to drain and stabilise the shafts. I think when you combine contemporary knowledge and modern understanding, it really shows the scale of Stephenson's achievement. And like Mike said, he was hands-on as a project leader on this tunnel rather than being the directing intelligence of the whole railway as well. And finally, probably the most pragmatic achievement is, if you go to Birmingham today, the West Coast mainland tunnel trains still pass through this tunnel. So those of you who are building railways today, you need to put in a concept, you should really expect people to be using your product in 2 centuries' time. So just finally, Mike and I would like to acknowledge all the help we've been given. Obviously, the library and archives of the ICE, the Library of the Geological Society and the National Archives is where this information is there, but it isn't easy to find, and Mike is amazing at finding some of this information. We'd also like to acknowledge contribution by others shown here. So with that, thank you very much, and I hope you've enjoyed our talk.
Thank you very much, Mike and Martin. Any questions, please? Could you say your name and affiliation for asking your question, please?
My name is Alistair Hughes, no affiliation, I'm retired. Could the authors say something about the state of the groundwater today? Does the present tunnel act as a drain? And I wonder how many litres a second come out if it does.
Well, I'll answer that. I'm only aware of public domain information, but you can go online and see that in the recent years, the track drainage has been renewed inside the Kilsby Tunnel, and it's not the first time it's been renewed in the last few decades. And my understanding is that the tunnel experiences seepage over a number of areas, and at least icing in winter and so on. But I don't know anything specific. Obviously, Network Rail would be the bodies that would understand that. My knowledge is I'm not convinced that anyone has done any intrusive geotechnical investigation there since Stephenson. I mean, if you go onto the BGS Geo Index, which records most, let's say public body boreholes and so on, there are not many dots in the vicinity of Kilsby Tunnel.
Mike McConnell, retired Balfour BT. Well done, Mike and Martin. It's lovely to get back to first principles again and not hear the word computer mentioned too often. Mine's just a very simple question. There was mention of these flat rod systems. Could you just elaborate on exactly what that was?
Do you want me to go back? I'll get the slide back up.
Yeah, well, essentially, in the mining industry, because steam engines were expensive, so the idea of having lots of steam engines on any mine site would have been prohibitive. So that they developed a technology which was fairly straightforward, really, which was. Yeah, thanks. So you've got the main steam engine house here, and it's driving a rotary wheel which is powering flat rods over a distance, which you can see here as well, and they're resting on, I'm going to say, tripods, which are capable of moving backward and forward to these effectively rocker pumps here, and they're driving the pumps up and down in the mine shaft. But the thing is, you could have your shaft here or over here, and you could have another one going off in the other direction as well. So you didn't have to. The capital investment in the steam engine didn't restrict your ability to pump any particular site. And in the context of Kilsby, it meant that they could actually make sure that the pumping shafts were well clear of the working once, because obviously you didn't want something pumping in the direct line of the tunnel. It's a very neat. I think it's a very neat solution, and quite simple. I mean, they're called flat rods because they're rods.
Was it pinned in the top?
Sorry.
Was it pinned in the top? Subject to a pin.
There are pins here.
No, but it wasn't paid. It's very old. I think it was developed sort of in Switzerland, was it? It goes back as far as the 15th or 16th century, and then it was introduced in the Cornish mines and so on.
Yeah. No, sorry, I thought you said pinned. No, they wasn't patented. It would have been pre-patent, I think, the knowledge of it. I mean, the Cornish miners and northeastern mining captains would have been in contact with mining experts from all around Europe, I think, from early times.
Yeah, in our paper, there's actually a little quote that we found in History Society where an 80-year-old man was recounting a visit to the site as a child, and he said how these rods were going backwards and forwards, making a huge noise and so on. And so I've looked at that picture for years, but I don't think that gives the whole thing. You know, think about all the number of bearings and things like that. It must have been screeching and rattling and stuff, you know.
There are photographs of the system in sort of industrial archaeology books, and the system still in place in the late 20th century in Cornwall, remains of it. So
David Hartwell, retired, failed. Fascinated, great stuff. Thanks, Mike and Martin. Fascinated by your description of a lake covering Warwickshire, which is my home county, and the concept that it may have had an outflow that left this channel. Now, such things occurred, particularly, for example, the tunnel I worked on a lot in Storbælt in Denmark, where at the end of the Ice Age, the North Sea broke into the Baltic via Storbælt, and we had a borehole that way down into the rock had cobbles and boulders in. And we hit it. We hit it in December 1993. And what was apparent was that this was where the high energy flow flowed into the Baltic and deposited these very large granular materials. And I also worry about the Africa to Spain tunnel, where, you know, if you imagine the Atlantic flooding into the Mediterranean, there must be some horrible feature there somewhere for that tunnel. So my question is, do you think that was the main outlet, or was it, because it doesn't look to me or sound to me as if it was the classic sort of outflow point of that lake?
Well, the answer is I'm just reporting in the paper that I led other people's work. I mean, if you look at the reference there is, the paper says, Fred Shotton and his key role in the Woolstonian and Deventing stage controversies. So I get I don't know how much genuine controversy there is in UK geology, but the Midlands seems to be a hotbed. There's a whole series of really fascinating papers in some quite obscure journals in the 60s where people are looking at you know, the nature of a sand exposure somewhere in the Midlands, and then it seems to me extrapolating out wildly to get a bit bigger picture. But I'm just going by the stuff. I mean, I'm working on a follow-up paper to this where we do look a little bit more at the geology. But again, we're not doing a field work. What we're doing is we're trying to understand you know, how credible it is that this this concept, as it were, of the lake feeds into the tunnel. But it goes to a point. It's a buried glacial channel, and as you agree, they're just bad news wherever you find them if they've got granular material in them.
Could I just add, perhaps, that you see Crick here? Well, there was a canal tunnel at Crick which suffered similar construction problems, which put Stephenson completely off the idea of going over an alignment up that way, which would have perhaps come through Northampton, which the good folk of Northampton may or may not have liked. But when you see this line here, it does seem a bit more than, you know, speculation that the previous generation of engineers had suffered similar problems on a very similar, very similar area, and you wouldn't know that it wriggled its way around in that way. But if you saw that today, you might not have built Crick Tunnel where it was either.
Question on the back.
Hello, thanks for a very interesting presentation. Richard Totty, currently not working, formerly of Bashi Saltranch. The location of the Kilsby Tunnel appears to be aligned with a county boundary, and county boundaries often align with river valleys or similar features. And while I've been off work, I've been on a two 6-week local archaeology courses for Surrey, North Surrey, where I live, and Guildford, where the presentations were taking place, is on an old droving line for a very old prehistoric droving line, and droving lines are quite often where roads and canals are located in modern times, because it's the line of least resistance which has been walked since prehistoric times. So I wondered if you were to look at archaeological records or LiDAR information, you might spot an archaeological link to the feature in terms of the archaeological the archaeological features. And then just with regards to the diluvial theory, my understanding of that is that it's probably to do with the theology around, as the other speaker at the front mentioned, the Atlantic flooding into the Mediterranean. And actually then that was a well-held belief from people in the Mediterranean and the old Holy Lands, which then migrated to people in northwest of Europe as that message spread over prehistoric times.
Thanks about the geology to the root. About the geology, what's interesting is that the papers, some of the papers that talk geology are the title of the published paper is An Excursion to Hillmarton in January 1842, where literally the paper in the Geological Society is a record of, including their journey there, of people going, and probably quite posh people by my standards, scrabbling around in the sand, but you know, as nearly all gentlemen, you know, amateur gentlemen doing it. But those were the records of further information being gathered. And of course, the hill at Kilsby, so the tunnel has to go through that hill because it's a bedrock hill. But there are two beds of sand exposed on it. But I think people, broadly speaking, these are pockets or surface things. And it comes back to the lack of, nowadays, everything in geology is about conceptual model. There was no pre-construction conceptual model. And furthermore, geomorphology would possibly have helped. Do you want to talk about the root side of things, Mike?
Yeah, well, I think one thing to note is that if you look in the parliamentary evidence, people like Forster and Stephenson were obviously asked by opponents and supporters of the scheme. And the sort of things they were looking at for the sort of things you're describing in a sense. They were looking for evidence of springs and old watercourses and talking to people about what they remembered. So there was I mean, sorry? Yeah, sure.
I mean, that one?
The kind of salmon-coloured pink blob to the southwest of the tunnel alignment.
Yeah, the glaciofluvial deposit. Yeah.
To my mind, kind of would scream alarm bells these days, because the interpretation of that would indicate lots of discontinuities.
Yeah, but you're looking at a map that didn't exist.
Sure.
That
was in its infancy at the time, but there, as you say, had Robert Stephenson happened to meet Mr. Smith in the pub one day, they might have been able to have a conversation and gone and mapped the hills and figured out what was going on.
But again, remember, Smith's map, broadly speaking, is bedrock, which comes back to the work by Boyd Dawkins, that the equivalent of U-lot in the 1850s, you wouldn't have had the access to the consideration that it was even relevant. You know.
I think that little quotation I gave from LeCount about going to look at the spoil, I mean, that was the little geologist's outings would have been to go and see what you found, and then you'd speculate about why there were fossils in there or whatever. And once you'd had a look at a lot of these spoil heaps, you might start to develop some kind of better understanding. I mean, both with this job and the Thames Tunnel job, I started out very sceptically about it, because you can read accounts of, well, the failures of previous attempts to tunnel under the Thames and the canal tunnel experience. But what strikes me about everything pointed to a continuity in the strata. When do you carry on? And then you sink a shaft, and lo and behold, it's much worse than you dared imagine.
And in reality, how many years from start to finish of the tunnel with all the problems?
Well, there was a year out of 3 years, so
yeah.
it's...
But I mean, I don't know how quickly you build a 2-kilometre tunnel in central England these days. It might not be that quick.
So just one last observation. At this sort of time in history and our geological understanding, wasn't this when Mary Anning was fishing out dinosaurs from the rocks in Lyme Regis, and most people thought they were dragons or monsters from the sea? Some of them were, but the interpretation was that there were all these mythical creatures roaming around. So that's the kind of uneducated thinking that was going on at the time. So Robert Stephenson was clearly ahead of his time in being able to interpret as much as he did from the ground.
Sorry. Ed Russell, Mark MacDonald, thanks for the really interesting talk. Along the similar line, just out of interest, like in you looking back at it historically, like obviously the information wasn't there from the time, but have you looked at the geomorphology? Do you think there, like geology-wise, there are hints, but is there anything in the geomorphology that's there that you've looked at that picks it out? The hill's got a bit of a dip that kind of alludes to the fact that something's not quite so solid in that area, but is there anything else in the wider region that...
No, I mean, I'm not remotely capable in geomorphology, but I have, to others involved in the area, suggested that that's what it needs. That's the absence of, to my knowledge, of what's been looked at. It's never been looked at geomorphologically, and maybe that would reveal things relevant to future works, because obviously I'm sure the tunnel will have to have future works done to it to deal with the water issues. But there's two things. There's how do you inform the future of it? See, I've no idea whether this buried channel, does it cross the tunnel at right angles? Is it very oblique? Is it a dead end? To go halfway in? There's no information that I'm aware of in the public domain about that, and I think a geomorphologist nowadays would certainly help.
Paul Perry from Houston Consulting Engineers. Just following up on those last couple of questions, is there anything now that is worth following on from your work that you've done to try and look more into the detail of this problem? I'm thinking of, is it worth doing a supplementary boreholes and actually looking at the groundwater where it is today, and then maybe going back to Network Rail and suggesting them what they need to do with their trap drainage in 30 years' time or 40 years' time when it gets inundated with all the leaking through the brickwork. I mean, I've worked on a number of old existing brick tunnels recently, and of course the records are poor, as I think you've got some great records you found here, but there's always leaking through brickwork, and there's always that debate about, what is the structural integrity, what is the earth, what are the pressures surrounding it, and what you need to do to operate and maintain it. I just thought, is there something physically that you could do now, following on from your work?
The last Network Rail report that I've seen,
Sorry, I should have said money's no object. No. But what I will say is that you don't need to feed your stuff into any computer, Zootech or Safety Base or any other stuff you get involved on major projects these days. I was just when I was
right, we're looking at this some time ago. One of the Network Rail contractors showed me a 2003 report where some of these issues were being looked at. And I don't know, and Martin obviously didn't either, know what the current situation is, because it didn't really tell me how much water was being pumped out. They just renewed the drainage system following that. But when tunnels like this were being built in the 18th and 19th century, the better built ones generally had parallel drains alongside, done in as a heading. It's obviously been quite challenging to do that here, as they discovered when they're trying to do drainage adits. But at Blisworth, which was 1805, I think, finished, that was the first tunnel where the alignment was drained by parallel drains alongside. So I think people were aware of these approaches when these tunnels were being built. It's a case of whether they could do it in the geology they came across, I think. I've seen reference somewhere to this bed being a mile across. I can't remember where I read that. But I don't know which way it's running either.
I mean, I think the simple answer is what they need a good conceptual model. And that's going to tell you where's the groundwater level, is there any gradient to it, how extensive is this bed. And that's currently absent because I don't think any major geotechnical works have been done on this for several decades. And I imagine at some point there'll be a driver when it will become slightly more urgent than it currently is, and then we need to go back to fundamentals, of let's look at the data. There'll be an intrusive element, maybe the geophysical element, maybe even trace a test to see where, because I'm aware the tunnel is receiving a certain amount of water, and it's nuisance water. No one's getting flooded out, but calcites build up, icing during winter, because obviously there's overhead lines through it, and they ice up. So yeah, back to basics, I'm afraid.
Okay, so I wanted to ask a fascinating, so amazing speech. Sorry, it's Yuli from Tensor and also BGA Vice Chair. So I wanted to ask what happened to this tunnel, but I didn't want to sound ignorant, so I went into the good old Google. And apparently this tunnel just reopened on 18th of May 2020 after 2 weeks of reconstruction of plugging leaks. And they just changed the tracks, so they've done it. Paul, and it's fascinating.
But they've done it several times. I don't, just on track record, that won't last 20 years. If you go back, they certainly did it in the sort of not long before the turn of the century, and they've done it before. So I think they have done it, but it's the whole sticking. I think sticking plaster would be the phrase I would possibly use.
Yes, it says because of its age, water leaks through the 183-year-old tunnel's walls had caused the track to flood and degrade. So now they made it waterproof and they changed the tracks, and they save 82 minutes in delays every day. And that happened in 2020. And that's astonishing that almost a 200-year-old tunnel that we just showed us being built in an incredible way is still in action and is still usable, and it's still, with a little bit of maintenance, it serves people. That is astonishing. So thank you.
Thank you, Julie. Giulia Viggiani, University of Cambridge. I have just a very small curiosity, still about water, but not now, more during construction. So I don't remember exactly the figures. It was gallon per minute or liters per second. It seemed a significant amount of water that was being pumped out. What would be at the time the strategy for the disposal or management of all this water that you were pumping out? Because that's a major issue when you do pumping works today. Like, can you recharge the groundwater at some distance? Do you put it in the sewer? So what would they do then? Because I don't have a clue.
I think in Martin's paper he refers to an aerial survey where you can see possible former drainage channels, but it's supposed to be, they did a deal with the canal company, because canal companies like water, particularly in the summer, and so some of it was routed away to the canal.
So basically, we identified, so this is the quicksand area, You can't really tell from the LiDAR or the satellite images where the pump stations were, but they're clearly here. And this watercourse just looks suspiciously straight down the hill. So our hypothesis is that this was built, then it picks up this existing watercourse, then there's a canalised watercourse that runs alongside the railway that conveniently goes to the Grand Union Canal. So we have no evidence. There's evidence that Stephenson mentions in a report that he was talking to the Grand Union Canal to give them the water and they'd want it. But this is one of our hypotheses, shall we say.
John Goodyear, no affiliation to the BTS. Following on from that last question, when the groundwater started being pumped, was there a filtration system of sorts to separate the quicksand? Or when the water was being disposed of, is it a case of there being a large quantity of solids as well to essentially shift?
It's a good question. There's no evidence of that. I mean, we haven't mentioned that particularly the pumping shafts were made from timber tubbing. And there's a great way to visualise what timber tubbing is. It was like a well-made barrel where you have hoops or curbs and vertical planks. And I can visualise in my mind that nowadays we have perforated well screen well constructed. The gaps between the planks would have to be filtered, and then these are big shafts, not well. So if you get a few cubic feet of sand in the bottom, it will come through. So a gut reaction is I don't think it was an issue, but I suspect because it was actually a well-engineered system for the time, I bet you they didn't pump much dirty water.
No, I mean, I think I'd agree with that. The lookout was a great one for statistics. I mean, Stephenson compared the job to the Great Pyramids of Egypt. So I think if there'd been a lot of sand coming out with the water, he'd have measured it and told us how much it was. So I don't think it was a significant issue.
Royce Logan, unemployed. You mentioned Blissworth. Can I just point out that the problem with the water there was very, very different because it was the water in the overlying sandstone that was weakening the clay that they were driving the tunnel through. And in fact, as you mentioned there as well, the canal company wanted to keep it because that's a head pond in the canal system. I worked there on the reconstruction of the middle section. It was deteriorated because of the water, or the water deteriorating the clay. And it's the only tunnel I've ever worked on where there was a requirement for it to leak. We had to connect into all these little drainage heads as we progressed along the tunnel. If you go through on a boat now, you'll still see the little windows where it comes through. The other point someone else mentioned about the deterioration in these very old brickwork tunnels. That's something I know a lot of studies are ongoing. I did some work to assist one of the contractors who was doing a study for Network Rail a few years ago. There were a couple of things that we just kicked around. Kilsby was one, because of this long-term deterioration problem. And as Paul mentioned, the one question you've never got an answer for when you're looking for things like that is what the real cost is to the railway of disruption or having, as someone else mentioned, avoiding downtimes, avoiding stoppages. If you were driving that tunnel today, a modern TBM would have romped through that and you probably wouldn't have noticed it. There was a paper back last year by Jackie Skipper about the infill buried feature that they encountered on the Lead Tunnel. And the machine went through that without knowing about it. The only reason they knew they'd gone through it was the guy on the separation plant noticed that the material coming off the screens changed in colour. So it's a great program, great presentation, very, very interesting. When you were talking about the long links from the steam engines, that's very much the way that railway signals operated up until the introduction of electric light signals. What was that in the 60s?
Right. Okay, we'll wrap up the questions there. Thank you very much, Mike and Martin, for your presentation. Right, I've got a few announcements before you were allowed to run downstairs. Just to remind you all that pre-ordering for the 50-year BTS book is still available. There's a lot of, well, there were definitely lots of cards downstairs to be able to scan in the QR code and order your book. Pre-ordering is open until the 31st of May, so please get the orders coming in, please. Right. It's all right. Some slides have disappeared. Right. Thank you very much to our three food and drink sponsors, Coffey, Stuart Wells Limited, and WJ Group. So we'll enjoy the effects of that downstairs in a few minutes. Meetings going forward. Thursday, 16th of May, is the BTS AGM and the combined May meeting, and the presentation is on Snowdonia Visual Impact Provision, a project overview. On the same day, the young members of the BTS have got a tunnel instrumentation and monitoring workshop on the afternoon. So members, BTS young members can register for that, and priority will be given to the actual members. Moving on, 30th of May, the young members have a spring social, a tank and paddle at Bishopsgate. I'm not quite sure what that engages, but it sounds a little bit wet. Perhaps you need a bit of dewatering there. There are still tables available for people for the BTS annual dinner. Deadline to provide any details about the various table is the 29th of April, but the dinner is on Friday, the 10th of May. You've got to turn up to hear my speech. Going into July, it's the BTS Design and Construction course, 5-day course, being held at Warwick. Places are disappearing quickly, and we are limited this year because of accommodation issues elsewhere, or they've got a huge other conference that's taken so many of the rooms in the Hall of Residences up. So please look to see who would benefit from being on that course. Going into next year, at the moment, people are actually in China preparing for the Chinese ITA conference. Next year, it's going to be in Stockholm, and the BTS is offering 2 bursaries. So please have a think if there's anybody that would benefit from that. The deadline is the 30th of April for applications. We've got opportunities to represent the BTS on a BSI committee. So we are looking for people to represent the BTS. So if you're interested in any of these particular areas and reviewing and commenting on documents on behalf of the BTS, please contact Bethan, who's down here in the part way back, or email through the BTS at the ICE, and we'll get the information over to Bethan. We've also got the opportunity for a partly funded by the BTS a PhD studentship at Nottingham. So we're looking for a candidate for this. So if you know anybody that this would suit, please could they apply to us, and we will pass on their information to the relevant people. The full details are up there. Just give you a chance to read it. Couple of BGA announcements. Seminar on Wednesday, the 1st of May. Session 3 on groundwater considerations. So there's an opportunity to register, and the QR code is there for people to access it. Another BGA future event, chalk characterisation for and driven pile behaviour at chalk sites on the 16th of May here at the ICE. Last but one is the BGA annual conference and AGM is on the 12th of June, whole day event from 9 o'clock in the morning till 7 o'clock, again here at the ICE. And finally, just saying again, the book is available for pre-orders. Sarah's at the back there with some cards with QR codes on, so you can't escape. And at that, thank you very much for this evening. Thank you very much for our presenters, and we'll all adjourn downstairs for the food and drinks. Thank you.